Hello and welcome to section 3.3 where we're going to talk about derivatives of trig functions. So we've seen some differentiation techniques for polynomials, exponential functions. We talked a little bit about product rule and quotient rule, keep those in mind. But now we're going to hone in on the trig functions and how we differentiate those. So right off the bat, there are 6 trig functions that we are familiar with. And we'll start with sine of x. That's typically, one of the nicer ones that we deal with. And if we're looking at the function y equals sine of x, then y prime, our first derivative, is going to be cosine of x. And similarly, if we start with cosine of x for our function y, then y prime is going to be negative sine of x. Watch out because there is a negative involved here. And then if we look at the ratio of sine of x over cosine of x, we build the tangent function. So if our function y is equal to tangent of x, then y prime is equal to secant squared of x. Now, we can look at the reciprocal functions as well. When we look at cosecant of x, cosecant is the reciprocal of the sine function. So if y is cosecant of x, then y prime is negative cosecant x times cotangent x. Okay, you can see that the reciprocal functions are a little more involved. Secant, when we look at the function secant of x, is the reciprocal of cosine of x. So if y is secant of x, then y prime is going to be negative, jump into the wrong one there, secant of x times tangent of x. Again, you can see it's a little more involved. And secant actually, when you look at secant of x and you differentiate it, you get secant tangent, you kind of get a little bit of that same function back again. And then the last one will be cotangent. If y is equal to cotangent of x, which is the reciprocal of tangent of x, then y prime is going to be negative cosecant squared of x. So keep in mind what you're starting with. Right, you're starting with all these functions on the left-hand side, and you're getting all their derivatives on the right-hand side. You can see that when you differentiate a trig function, you get a trig function back, or maybe a multiple of trig functions. Or in the case of tangent, you get secant squared. In the case of cotangent, you get negative cosecant squared. And so some of them are a little more involved than the others. Sine and cosine being, I would say, arguably the easiest of the two to work with. But those are our derivatives for trig functions. And those are our 6 trig functions. Later we'll look at the inverse trig functions and things like that. But for now, we're just sticking to the basic 6 trig functions. Yeah, I'll need the room. So let's take a look at using some of these derivatives and some different problems, different scenarios. Let's say we want to find dy dx, which of course means finding that first derivative. And we'll do a couple. Let's say y equals sine of x plus cosine of x. And before we even jump into that, a quick word on notation. Right, if I drop these parentheses, it's just understood. Right, this is a function sine of x, cosine of x. But I like to be a bit more clear whenever possible. It doesn't take too much more effort to put those inside the arguments like that, so it's clear what we're looking at. If this is our function y, Y prime is, well, we still have the old rules of differentiating term by term. So when we're separated by addition, I just have to look at sine of x and differentiate it, and I get cosine of x. And then plus, now I have to differentiate cosine of x, but I get negative sine of x. So adding negative sine of x means I just subtract sine of x. And that's it. There's our derivative. Oops. Let's get our y equals going first. So if we look at another one, let's say we're looking at the function y equals 10 times tangent of x. Now 10 is just a multiple. So when we differentiate the multiple of a function, we can just take the multiple of the derivative of the function, right? We have that old rule, so we can just say y prime is going to be equal to 10 is just a multiple, which means my derivative is going to be a multiple. And then if I differentiate the tangent function, I get secant squared of x. So there's my derivative. Again, where the multiple just comes along for the ride. Let's take a look at y equals 3x to the fourth plus e to the x minus cotangent of x. So now when we differentiate this, again, term by term by term, we're familiar with this stuff. So that means we're going to get y prime. I differentiate this first term here, I get 12x cubed. That's just going back to the old power rule. Differentiate e to the x, I just get e to the x. I'll add that. Differentiate negative cotangent of x, I'm going to get negative cosecant squared, which is plus cosecant squared of x. All right, so there already is a negative built in here, and we saw that when we differentiate the cotangent function, I get a negative cosecant squared of x, which means there's going to be minus negative cosecant squared of x. So I'm just writing plus cosecant squared of x to save some time. Separate that. Let me show you something funny that happens with trig functions. We'll say find the 10th derivative of y equals cosine of x. And you think, oh boy, this is going to be a task, but watch what happens when we look at, and sometimes I like to just write down these functions like this, and then I'll explain myself in a second here. Sometimes when you come across these, there's a trick to this problem that basically says when you differentiate y equals sine of x, you get y prime is cosine of x. Or if you start with y to be cosine of x, y prime is negative sine of x. And then with this extra negative symbol here, let me emphasize that, I forgot it there. If you start with the function y is negative sine of x, well, the negative is going to stay, and differentiating sine of x gives you cosine of x. And then, of course, if you have negative cosine of x as your original function, this negative stays, and then differentiating cosine of x gives you negative sine of x. So you're going to have a negative sine of x, which is back to sine of x. So they have this nice pattern that you can follow. So you really just need to figure out, okay, where do I start and where do I end? You don't have to take this function and do y prime, y double prime, y triple prime, fourth prime, fifth prime, sixth prime. You don't have to go all the way up to the 10th derivative. Figure out where you start. Our starting function is y equals cosine of x. And then just differentiate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. And that means this is going to be y prime. All right, so it's a nice thing about these sine and cosine functions and the way they just kind of have this nice pattern to them. So y to the 10th, that's not power, that's the derivative, right? We don't want to do 10 slash marks. That would just be really cumbersome to read. Is negative cosine of x. All right, so if you ever come across sine of x or cosine of x and you're asked to find, it may not be a 10th derivative, but maybe even, fifth, sixth, seventh at that point. You might just kind of recognize the pattern and get to that sixth, seventh, eighth derivative really quickly. So I just wanted to show you that nice little trick that we have for sine and cosine. The other trig functions, of course, are a little more involved when you take their derivatives. So you may actually have to roll through all 10 derivatives, keeping track of things, which means it could get really nasty really fast because of the way we have to apply product rule and things like that. Okay. Just kind of going back through and looking at a couple more problems. Let's say we start with the function y equals x squared times tangent of x. And our goal is to find dy dx, aka the first derivative. Now, we do need to be careful about one thing, and that is there's no plus or minus in between here. I am taking the function x squared, and I'm multiplying it by the tangent function, tangent of x, which means I do need to use a product rule. So do be very careful. We're going to have to implement the product rule here before we go anywhere with it. So let's start out by giving us some more room. We'll slide over here, and we'll say y prime is equal to, recall that our product rule has us take the derivative of the first function, which is 2x, multiply by the original second function, which will be tangent of x. Then I get a plus for my product rule, and I take the original first function, which is x squared, and then I multiply by the derivative of the second function. The derivative of tangent of x is secant squared of x. And I'm putting lots of parentheses around so you can see that when I take this, I am differentiating the first one, but I am keeping the original second. I'm keeping the first one. I am differentiating the original second there. Or differentiating the second function, I should say. And again, just to kind of try and clean things up, nothing's going to clean up very nicely, but there is a common factor of x. These trig functions aren't the same, so I can't factor that out. Best case scenario, you could clean up some of the parentheses and things like that. And maybe get it down to this. So, again, knowing that we still need to use product rule from here on out, or quotient rule from here on out, ensures we get the right derivative. And in fact, I'll do a quotient rule now. And I'm trying to do a little bit of, a mix of a whole bunch of different trig functions. So you can see them being differentiated. So again, we're going to have to rely on quotient rule because this is the quotient of two functions, which means I'm going to look at y prime. The quotient rule says I need the derivative of the top. Well, if I differentiate the secant function, I get secant of x times tangent of x. And then quotient rule says I multiply by the original bottom, so I'm going to multiply by x. Quotient rule gets the minus. I'll put my division bar in here so we can keep track of things. Now I want the original top, which is secant of x, times the derivative of the denominator's function. Well, derivative of x is just 1. I'll put a 1 there so you can see I'm multiplying by 1. And then don't forget, quotient rule has us square the original denominator function. So it's not going to be anything that I have to do to differentiate this or anything. I just square it and write it downstairs. All right, so derivative of the top times the bottom minus the top times the derivative of the bottom, which is just 1 all over the bottom squared. And there's not too much we can do with it, but there is a common secant of x that we could pull out. And that'll leave us with, I'm going to switch it so it says x times tangent of x. That way it doesn't look like both those x's are in the argument. I'm going to get rid of that 1 now and just write, sorry, I'm not going to get rid of that 1. I got rid of the secant, so I'm going to just write the minus 1. And then, of course, x squared in the denominator. Now, there's no multiple of just x in common in the numerator. One of the terms has a multiple of x, but again, there are 2 terms in the numerator that we must see. And these x's are all in the arguments. They do not cancel with x's outside of arguments. So these are true multiples of x down in the denominator, but I don't have a multiple of x to cancel out in the numerator. I only have one buried in one of the terms, not common across everything. So no canceling. Unfortunately, we're just kind of stuck with that. And this isn't any sort of identity that we have from trig, x tangent x minus 1. That's not an identity for anything. So we're just going to leave it. That's the best we can do to clean it up. Okay, now I will see, maybe I'll go to the textbook and see if I can steal a random problem here. Here we got a little bit of this. Ooh, here's a good one. And this involves some trig, and it asks for what values of x does the graph of f of x have a horizontal tangent. So it's asking us, when is our graph going to have a horizontal tangent line? And the function that they give us is f of x is equal to e to the x times cosine of x. All right, so you can get a graph this function to get an idea for it. But ultimately, it's asking for, when is this function, f of x, going to have a horizontal tangent? When you see that word horizontal tangent, that means that you want your slope m to be 0. All right, you want the slope of the tangent line to be 0. So I'm just marking that down so we can all see what our goal is, what we actually need to get to. All right, so that's not part of my solution or anything. I'm just identifying, oh, this is what my brain needs to do. My brain needs to find out when the slope of the tangent will be 0. That's what they mean by horizontal. Well, first of all, to get the slope of the tangent line, I need a derivative. So I would have to go ahead and differentiate this. All right, this is a calculus class. Basically, first step is almost always to differentiate it. Right? So it is a product of 2 functions. I'm multiplying the exponential function e to the x times the trigonometric function cosine of x. So I do need to apply a product rule and get the derivative of the first times the second plus the original first times the derivative of the second. Be careful, because when you differentiate cosine, you get a negative sine of x. So that means that my derivative is e to the x times cosine of x minus e to the x times sine of x. Now my goal here is to take this f prime of x. This derivative tells me the rate of change. I want my rate of change to be 0 because I want to identify horizontal tangents, no other tangents, which means I need to set this derivative equal to 0. I need to force my derivative to be 0, and I have to find the x values that make that happen. So we're not doing maybe what we did before. We would plug in a certain x and it would tell us some sort of slope. No. Now I'm telling the slope, and I have to work backwards to identify that x that I need. So in order to do that, first thing I'm going to do is I'm going to factor out e to the x because it is a common factor. And of course, when we try and solve equations, What do we do with them? Well, we factor them and set each factor equal to 0. So that means I'm multiplying two things together. Either e to the x is 0, which will never happen because here is the graph of y equals e to the x. Right? This function is always positive. Right? And we're not transforming it in any way, shifting it up or down. It has that built-in asymptote. No matter what number you plug in for x, you're never going to get 0 out of this function. So that's something that we just need to know. That is a property of the exponential function, which we have dealt with the exponential function for quite a while now. We should be familiar with that property. So that gets rid of any choice there. I try to set this equal to 0, and I get no results. So now I have to try and set the other piece equal to 0. Now I have to try and set cosine of x minus sine of x equal to 0. Well, this takes us back to our trig days. Right? So now I'm solving an equation involving trig functions. So I want to see where cosine of x and sine of x have the same value. I'm just adding sine of x to both sides so that I can identify where this equality holds. Well, I'm not graphing these functions. I'm actually just kind of drawing out the unit circle here. Remember that sine and cosine are both positive, right? And they both have to have the same sign. It's not like one's positive cosine, one's negative sine. When I add sine of x over onto both sides, and it cancels out on the left. This is the equation I'm solving, which means I'm looking at this point here. And sine of x and cosine of x are both negative and have the same value at this point over here. So what must x be? Well, x has to be this angle, which in this case is pi over 4. Right? Sine of pi over 4 is root 2 over 2. Cosine pi over 4 is root 2 over 2. And then down here at 5 pi over 4, sine of x, or sorry, I should say sine of 5 pi over 4 is negative root 2 over 2. Cosine of 5 pi over 4 is negative root 2 over 2. Therefore, we found our x values. Thus, when x equals pi over 4, or x equals 5 pi over 4, the function f of x will have a horizontal tangent. So it's a good mix of, reusing some old trig, and this is not a terribly hard equation to solve, right? We didn't have to do anything fancy with it. And also identifying that this guy is always positive and we never run into a situation where that will give us a 0. So at that point, we can ignore the e to the x function. And just for fun, go back and look at the textbook and see what else they offer. There are some limit questions in there. Let me see if I can focus on a limit question. Oh, here we go. Let's go. Find the limit as x goes to 0, sine of 5x over, I'm just going to change it to a different number. Let's say 7x. And so, getting away from the derivative stuff for a little bit here at the end, but that's okay. We'll look at some limits with trig functions in them. And in this case, it's not going to be like a direct evaluation where I can just plug in 0, because if I put 0 into this argument, I get 0 in the argument. That means I'm taking sine of 0, which is 0 up top, and then I'm plugging in 0 downstairs and getting 0 on the bottom. So right away, if I do go to plug in x goes to 0, I get something silly like this 0 over 0, which is not telling us anything. That's not a number. That just tells us we got to go back and try something different. And there's nothing I can really do to like factor or anything like that. So instead what we want to do is play with it using this nice little trick. Maybe let's pick theta. I gave you this limit a couple lectures ago when I talked about here are some popular limits that we usually see. We will actually get a nice trick to prove this. I shouldn't say trick. It's a nice actual property that we can use to show that this limit is 1. But for now, I'm going to use this fact in the solution of this problem. Right? So I gave you this limit as one of those like popular limits that people see quite often. So I'm going to use that popular limit. So let's start by saying a limit as x goes to 0, sine of 5x over 7x. If I try and evaluate it directly, I get nothing. I get nonsense. So I'm going to have to play. And the first thing I'm going to do to play is I'm going to take this 7x in the denominator. And essentially what I'm going to do is I'm going to multiply by 5 and divide by 5 because I see 5 in the argument here. I'm going to show you what I mean. I'll use a different color. There you go. It's the old multiply by 1 trick. I have not changed this ratio at all. I just multiplied the denominator by the number 1. So I have the exact same function. But now what I'm going to do is I'm actually going to swap over one of these 7s with one of these 5s. So I'm going to write 7 over 5 times 5x. Still multiplying by 5 and dividing by 5 with 7x. Still multiplying by 5 and dividing by 5 with 7 times x. Yeah, so everything's still the same. But I've rearranged them in such a way that now I can have 5x and 5x together top and bottom. So essentially what that does for me is it allows me to look at this dividing by 7/5 as multiplying by the reciprocal 5/7 times sine of 5x over 5x. So I've essentially pulled this 7/5. Instead of dividing by 7/5, I'm multiplying by the reciprocal 5/7, right? We don't divide by a fraction, we multiply by the reciprocal. But this is just a constant multiple, so I can write that out front using our limit properties. And now I'm looking at this limit sine 5x over 5x. Now here's where I'm going to pause and make a substitution. Let 5x equal theta. And so 5x is just some quantity, top and bottom. And as x goes to 0, so does 5x, which is theta. This means that as x goes to 0, theta must go to 0 as well, because if the left-hand side is 0, the right-hand side also has to go to 0. Now this allows us to take this limit. That's the limit as x goes to 0. Well, let me write my 5/7 out front. Can now be rewritten with this substitution in place. 5/7 is a multiple. I'm taking the limit as I've made my substitution. Instead of x going to 0, theta is going to 0. And instead of 5x, I'm just writing theta. Again, in the denominator, instead of writing 5x, 5x is exactly theta. I'm just writing theta. And then you can see my limit pops up. The limit as theta goes to 0, sine theta over theta is 1. That means this piece, limit theta goes to 0, sine theta over theta is exactly 1. But I do still have this multiple of 5/7 in the way. So my limit, or works out to be 5/7. And this limit is equal to this limit, so therefore I can just keep backtracking all the way to get to my original limit. Therefore, the limit as x goes to 0, sine 5x over 7x is equal to 5/7. Simply by backtracking. And what this actually does is it brings up something nice. You can recognize the pattern pretty quickly. There's 5 in the argument and 7 in the denominator, and I get 5/7 as the limit. So what we can do is we can actually go a little further. Now, it might take some showing by replacing 5 with the letter A and replacing 7 with the letter B, and then like multiplying by A over A and doing it in terms of a more general A and B situation. In fact, give that a try if you want, and you'll prove that sine of AX over BX is A over B, which is a really nice result because it just kind of takes this concept and extends it even further. The limit as x goes to 0 of sine of AX over BX will always be the ratio A over B. So that's actually something that we can kind of take for granted by just taking a simple problem with numbers, like actual fixed numbers 5 and 7 in it, and replacing them with something that's just A is a real number, B is a real number, and computing from there. Let's see what else we got. Yeah, I think that's good. I just wanted to show you this nice problem. Should be a problem that almost everyone in a Calc 1 class covers, and then we get that nicer result out of it for free. So, trig functions, since this section is just dedicated to trig functions, that's all we really need for this section is how to differentiate those 6 trig functions. But remember, you're now applying that on top of everything else we had for polynomials, for exponential functions, product rule, quotient rule, and all that good stuff. Now, you'll notice that we still don't have the ability to differentiate every function we come across. And that's where the next section picks up the more complicated functions. And what I mean by more complicated functions is, more specifically, I guess I should say, the composition of functions. We still don't know how to differentiate things like sine of x squared plus 2 over 5x. Right? Because there is a composition of functions that's involved here. And I can't just differentiate this using the quotient rule and then just shove a sign in front of it, right? That's meaningless. Then you're not touching the actual sine function when you differentiate. So things like that are a little more complicated. Also things like, let's say the square root of tangent squared of 2x plus 7. Right? What is y prime? Things are a little more complicated in that sense because I'm dealing with a square root function. I'm dealing with a tangent function that has been squared. I'm dealing with a 2x. That's not just x in the argument. That's the function y equals 2x. Plus I'm adding 7, which means I can't take the square root of this and the square root of that and add them separately. I'm stuck all under the radical. So things like that are a little more complicated, and that's where the next section picks up. So make sure you're good at this point. Practice polynomials, practice exponential functions, practice trig functions, differentiate. Practice your product rule and practice your quotient rule. Because if you go into the next section, 3.4, without being 100% firm on all those types of differentiation techniques, then 3.4 is going to be really rough. Because without knowing the previous rules, you can't do the rule that is given to you in 3.4. So fair warning there. this is a good point to say, let me practice everything up to 3.3 and make sure I'm solid, and then I'll get into 3.4. Trust me, it'll make 3.4 just a little bit easier. Yep, so that's it. I will see you in the next section for the chain rule.